Okay, I think we are ready. So let's start today's class. So thank you for being here. So today we will talk about describing nodes. So last class we were mostly talking about how to characterize a network as a whole, but this time we are more interested in who are the interesting nodes. So we can measure node importance using so-called centralities. So centrality is actually not a very good term because it's not in general about being central in the graph in terms of being, I don't know. Well, so I will present some centralities which actually can be interpreted as being central, but some others are measuring something different, which is more like some type of properties, characteristical properties in the network. So the first one we have already discussed last on Tuesday is the degree centrality. So degree centrality is just a number of connections that you have. You probably remember that. This, so yeah, you can, I already explained how to compute it. You can just make the sum of the column or the line of the adjacency matrix, for instance, or just count in graph terms. And it's often enough to identify the important nodes. So for instance, if you think about a network representing interaction between people in a movie series or in a book, well, the characters that have the most interaction with others are probably the most important ones. Okay, that's a way to identify. The largest airport in a network in which nodes correspond to airports and links correspond to connection between them. Probably the airport with the most connections are the most important ones. And of course, in an online social platform like Twitter, the node with the most connections are also probably the most important ones. But not always. So for instance, if you look at Facebook or other platforms and you look at the number, for instance, of outgoing links, and in Facebook, so with the most friends in bidirectional friends, the one with the highest value of degree are probably spam. Same thing on Wikipedia, probably the pages with the most links, the most hyperlinks to other pages, if you create this kind of network. They are just pages with list of everything that happened in 1998. And maybe these pages are not the most important in terms of how interesting is their content or how often they are browsed by people. So degree is often a good sign of importance, but you can have nodes with a very high degree that actually are not that important in the network. So we need to define other ways to characterize the position of a node in the network. So another one that we have already discussed is the node clustering coefficient. So if you remember, it corresponds to the density of the neighborhood of a node, or the number of triangles that are closed among all triangles among the neighbors. I warned you that you have to be careful because if you have a degree of 2, then the value can only be 0 or 1. Either your two friends, they are friends together and it's 1, or they are not friends together and it's 0. While nodes with a high degree, they tend to have values between 0 and 1, but neither 0 nor 1. So ranking them is not meaningful. It doesn't really make sense to look at the top degrees by clustering coefficient, while it makes sense to look at the top nodes by degree. One interpretation of the clustering coefficient is that it can be used as a proxy for belonging to communities in the network. In sense that if nodes belong to a single group, they will tend to have a high clustering coefficient. So if you I don't know, we consider your network only composed of the people from your current class, probably the people you know in the class, they also probably know each other. So if you belong to a single group, if you look only at your connection with people of your class, you will have a high clustering coefficient. Your friends are friends together. But if you tend to belong to several groups, for instance, if you're someone who have moved in many cities and you have attended 1 year in Paris, 1 year in New York, and 1 year here, then probably you have many friends you have friends from New York, friends from Lyon, friends from Paris, and they are not friends together. So if you belong to several groups, probably you will have a low clustering coefficient. So this value of clustering coefficient can be interpreted in this way. So the clustering coefficient can also be computed for edges in this way. So for those who are familiar with it, it's the Jacobi coefficient of the neighborhood. Basically, we can understand it very quickly with this, this figure in which you want to compute the clustering coefficient between this node and this one. And what you do is to compute how many of their neighbors are common neighbors. Okay, so this one has 1, 2, 3, 4, 5 neighbors. This one has 1, 2, 3, 1, 2, 3, 4, 5. In total, they have 8, right? Oops. Neighbors. Yes, 8 neighbors, and they have 3 in commons. So the clustering coefficient is 3 divided by 8. And some people propose some interpretation of that. So for instance, we can differentiate connection links that are integrative than compared with edges that are dispersive. So dispersive will mean that you will have this low clustering coefficient, and you are like between, it's an edge which is between groups, while an integrative link is inside a group. That's the generality. Okay, so we move to a different set of centralities, which are FARNESS, closeness, and harmonic centrality. So this one is really related to the notion of being central, like in a geographical term or in a geometric term. So the idea is to measure how close the node is to all the other nodes. So if you take a figure and you look at the center, the one property of the center is that it's the point which is the closest to all the other points in average, right? Because if you're at the periphery here, you're very far from the part of the figure which is on the other side. While if you're in the middle, well, you minimize your distance to all the other points in the figure. And in a graph, it's the same idea. You want to find the point here in this graph. That is, you see, you can measure the distance to all the other ones, and the highest centrality should be the ones which are in the center kind of the graph if you draw it like this. So to measure, to define this closeness, this notion of closeness centrality, we start by the FARNESS. So the FARNESS is simple. It's just the average distance to all other nodes in the graph. So to know the FARNESS of one node, you take this node, you measure all the distance to all the other nodes in the graph, and you take the average. And then you define the closeness as the inverse of the FARNESS. So just so that we keep the same order than for the degree centrality, for instance, we have this notion that the highest the value, the more important is the node. So we do the same, we define the closeness in this way. So the node with the highest closeness will be the most important in the network in some sense. So for instance, how to compute it? Well, here you have the detail. So the colors are not very good, but okay, you see that this one is a little bit darker. So this one is the one for which I'm computing the closeness centrality here. The numbers correspond to the distance. And so you have here the sum of the distance. So you have 3 nodes which are distance 1. You have 7 nodes which are distance 2. and you have one node which is at distance 3. So with this, you compute your closeness centrality like that. So for instance, you have an example in this figure where you have, I think, the city of Amsterdam. And the network is composed with each node is an intersection, and each edge corresponds to a road, a part of a road between two intersections. You compute the closeness centrality, and what you observe is what I was describing. So the red are the values most important. And what you observe is that the nodes of highest importance are in the city center, basically, because you have this circle, maybe half circle shaped. And so the most central are around the city center, the old city center of the city here. So we see that it allows to identify importance nodes in this way. So there is a variant of it, which is called the harmonic centrality. It's really the same idea, but instead of taking the inverse of the sum of distance, you're taking the average of the inverse of the distance. What is the interest of doing that? Well, it has one main particular interest is that you can compute it even if your network is disconnected. It means if you have several connected components, if you have a graph with several parts and no link between them, because otherwise it will be impossible to compute the. So you consider that you have an infinite distance in that case, and so you consider that 1 divided by infinite is 0, and so in your sum here you will have some 0, but that's not a problem. So you can still compute it, this value, even if you have several parts of the graph. You will just consider that if you cannot reach some nodes, well, they give you a score of 0. And again, how to compute it? So it's the same thing. We compute in that case 7 times 1 divided by 2, 1 times 1 divided by 3, because there is one node at distance 3. And all those at distance 1 give you this score. So you see that the score is a little bit different, but obviously the two measures are highly correlated. And now one which is very interesting. This one is very often used because it measures something which is quite different from the others. So already you see that between the degree centrality and this closeness centrality, you see that there are some similarities. So a node that has a high degree will have a good chance to be central in the network because it can reach many nodes quickly. But still, you see that it can be very different in some cases. For instance, if you have a network which is clearly organized with a core and a periphery, like a city, but you have some node at the periphery which is connected to many neighbors, then it will be far from all the others, but still it will have a high degree. Okay, so what we're interested is to get centralities which are really different from each other, and betweenness is often offer a different picture of the importance of nodes. So basically it measures how much the node plays the role of a bridge, and it's defined as the fraction of all the shortest path between all the pairs of nodes going through U. So the best is to explain it with a figure like this, in which we want to compute the betweenness of that node. So what we need to do is to compute all the shortest path between all the other nodes. Okay, so I compute the shortest path between this node and this one, this one and this one, this one and this one, and this one, and so on and so forth. So I compute all the shortest path between all the nodes. And I know that the number of those shortest paths is the number of combination you can make. So here it's 11 times 10, so all the pairs of nodes. So you have all the pairs of nodes. And on the top here, we will compute the number of those shortest paths that go through the node. Okay, so we want to know how many of these shortest paths are going through that node. And this tells you that if the node is on many of the shortest paths, then it has a very important position in the network, in particular in terms of diffusion, for instance. So you know that, for instance, if you remove that node, probably the node of highest betweenness, it will probably make the diffusion of information or the propagation of a virus or whatever that move in the graph, it will make it slower because this is the shortest path between many nodes. So if you remove it, you will make many paths longer. So here is the detail of the computation. So we know that we see that U is on the shortest path between all these nodes and all these ones. Okay, so that's why we have 5 times 6, because we have 5 nodes here and 6 nodes here. And we know that all the shortest paths between all of them and all of them are going through U. So this is the number of shortest paths between those nodes and those nodes. There is also one shortest path between this node and this node. That is going the shortest path. There is one of length 2, which is going by this node. So there is the other one is longer. And finally, there is twice half. We count half because between this node and this node, you have 2 shortest paths of equal length. You have this one and you have this one. So there are two paths of minimal distance. So you count only half of them because half of these shortest paths go through node U. So this is true for this pair of node and this pair of node. So on the contrary, obviously, you do not count this one and this one because the shortest path is not going through U. You do not count this pair because the shortest path is not going through U. And same thing for all the nodes in this clique, where all the shortest paths are going directly by a single link. Okay, so the only problem with that is that you need to compute the shortest path. So if you want to compute the betweenness for all the nodes in the network, you need to compute all the shortest paths between all the nodes in the network. And this is costly, but if you're interested, you can look at how these algorithms work. You will see that, yeah, it's costly. So sometimes when you have a large graph, we compute an approximate computation by defining some maximal distance at which we will accept to look. So if you take the same graph as before, which corresponds to the city of Amsterdam, and we look at the nodes of high betweenness right now, you see that the distribution of the color is completely different. And the nodes which have the highest betweenness, they are not in the city center, but they are a little bit everywhere in the city. So do you have an idea of what this betweenness is related to in that city in particular? Yes?
Biking routes.
So it might be related to this, probably, yes. But there is also another thing. Yes?
Bridge?
Yeah, bridges. Because in Amsterdam, you have a lot of canals. And so to cross them, often you cannot cross them at every road. And so they are some points of critical importance on which many of the shortest paths are going. So there is a lot of bridge because there is a lot of rivers and canals. You can also define an edge betweenness because on that one it was a node betweenness, but you can define exactly the same thing for edges. You will find the betweenness of an edge is how much of the shortest paths are going through that edge. And question here, what do you think is the, so it's a railway map of Europe. And do you have an idea of what is between the edge of highest betweenness here? Probably. several possibilities, but there is one obvious answer. Yes. Yes, exactly. Because if you remove this connection, then you completely disconnect this part from that one. So it means that if you want to go from anywhere here to anywhere else in Europe, you have to go through that single connection between the two. And we know that when there is a problem there, it makes big news, while even if some line is cut between some part of France and another, well, it's redundant, so you can still cross. So.
This betweenness somehow with flow algorithms?
With, sorry?
With flow algorithms, for example, with min-cut max flow or something like that. So for example, here we can see that this channel between UK and France is handling cuts. And so can we solve the problem of the betweenness with cuts and flows?
I'm not sure, sorry, to understand.
For the EDGE-BETWEENNESS,
yes.
Can we solve the problem with cuts and flows?
I'm not sure. Sorry, I'm not sure to understand your question. But maybe we can we discuss at the break? Yeah. Okay. Okay, so recursive definitions. So we have seen these measures of centralities. There is another category which is often used, which is based on different ideas, which is the idea of recursive importance, which is that a node is important if it's connected to important nodes. And there are several centralities based on this idea, EIGENVECTOR centrality, PageRank, and a few other ones. So the idea is that we would like to have a score such as each node has a score, it has this centrality. And then we want every node to send this score to the neighbors, and the sum of all the scores received by each node will be equal to its original score. That's why is written here, the score at the next step is equal to some normalization and the sum of, for all the neighbors, their score. So we normalize it to have a fixed point, but the idea is just this. And this problem can be solved intuitively by what is called the power method. So we initialize all score to some random values. Then each score is updated according to the desired rule until reaching a stable point. So you send to the neighbors, you make the sum of what you received, and you start again, and you start again, and you start again, until you converge. And why does it converge? Well, this is what is defined by the Perron-Frobenius theorem, which is true for undirected graph with a single connected component. So what we just described is called the eigenvector centrality, because that's exactly what is defined by the definition of an eigenvector. That if you take your adjacency matrix, so which define who is connected to whom, and you multiply that by an eigenvector which corresponds to the centrality of the node. So you have a vector of size n, and each value of the vector corresponds to the centrality of the corresponding node. And if you do that, then you go back to the same value with a normalization, which is that lambda. And so yes?
So whatever the centrality used to initialize the in the beginning, it always converges due to this theorem.
Yeah, due to this theorem, you can prove that it will always converge. So you can start with any random values, you do the process, and you converge to the particular case corresponding to the leading eigenvector. So there are several possibilities of these eigenvectors, but you will converge to the leading one. Okay. So this is the definition, but like that, we don't really maybe get a perfect sense of what we will reach. So intuitively, there is a problem with that. but we still see, so because we have decided that we are important if we are connected to the important ones, but then you see that it's the problem of the chicken and the egg. So you are important because you are important, but then the other are important because you are also important. So we see that it's a difficult problem. So that's why there is this convergence. But there is a limit with the eigenvector centrality, which is that it doesn't work well with directed networks. And we can see it clearly with a small example like this, because what you do at each step is that you compute the sum of what you received from your neighbors. But obviously, if you take node A, it has no incoming edges. So if it's directed, each node is sending its value to the neighbors. But here, A will thus receive nothing. So we might say, okay, it's not a big problem because if we receive nothing, we have an eigenvalue of 0. Maybe it makes sense. I have no incoming connection. My centrality is 0. I'm not connected to important nodes. But the problem is that in the next step, since you have, you will send 0 to all your neighbors. And you might note that B actually has a single incoming edge, and this incoming edge is coming from A. So in the next step, B will also have an eigenvector centrality of 0. And if you continue, you see that this node has only an incoming edges from A and B. So then this node also will have a value of 0, and so on and so forth. So there are some graphs in which it works. So only you can compute it only in the strongly connected components, which I have defined in the first course very briefly. So it's like a connected component, but for directed edges. So it means that every node can reach all the other ones following the direction of edges. So this is a strongly connected component, and in that case, it works. But still, it's a strong limitation. So that's why some people have proposed an improvement, which is the PageRank algorithm, which is actually just a generalization of eigenvector for directed networks. So this paper was published in 1998, and some of you might already know it, but maybe, so do you know who are the authors of this paper? Yeah.
The founders of Google.
Yeah, they are the founder of Google. And so if you look at the abstract of the paper, you see that in this paper we present Google. So it was really the founding paper that allows to create Google. So by the way, while reading this paper for the class, I was quite interested by some part of it, which are really funny when you read now. So first they explain why they choose Google, okay? But then there is this very delicious part when they say, so at the same time, search engines have migrated from the academic domain to the commercial. So up until now, most search engine development has gone on at company with little publication of technical details. So this causes search engine technology to remain largely a black art and to be advertising oriented. See Appendix A. With Google, we have a strong goal to push more development and understanding into the academic realm. So, okay, they changed their mind a little bit later, but in this paper, I was really motivated to create some very open and academic friendly search engine. Yeah, they even say we expect that advertising funded search engine will be inherently biased toward the advertisers and away from the need of the consumers. That was really at the core of creating Google, but then it changed. So yeah, they were young at the time, they were PhD students, so maybe it's normal. So actually, PageRank is mostly an improvement over the eigenvector centrality. What they proposed is that there is this problem of the source node in the directed network. So we have seen that if a node has no incoming edges, then it has an eigenvector centrality which goes to 0 and transmits to the others. So their solution is just to add a constant centrality gain for every node. Okay, simple. And this is just a change in the formula here, where they add this this parameter to add some constant gain. And then they have made one important change also, which is that we not with very high centralities give in the original version of the eigen centrality, each node send its importance to all the other nodes. So if you're very important and you are connected to, and you are pointing towards many different nodes, you will give your importance to all of them, even if some node is, if you point to 1 million other pages in the web, for instance, and one of these pages has only you as incoming edge, it will still be considered important because it is pointed by an important, very important node with a high value. And so instead of doing sending the value of doing the sum of all the incoming edges directly, they consider that your value of centrality is divided among all the nodes you're pointing to. So if you're on a list of reference and you're pointing to many different pages, then it won't give a strong importance to all of these pages because your importance will be divided among them. So this can also be written in matrix form, obviously. Actually, it will look like what I explained on the first class on this idea of a random walk matrix. So it's really linked to it. So you will normalize the matrix by columns, which means that you're dividing among your neighbors. So you're not, because the more value you have in the column, the more the more you normalize, the more you divide the values by a large number of values. So again, if you want to look at the data, I let it look quietly at home, but the intuition that you can have is that it's called a random walk with teleportation. The interpretation of the PageRank is quite simple, is that if you do an infinite random walk, so it means you start from a node, you take one of the, at random, one of the outgoing links among all the, you take at random among all the outgoing links, and you repeat that. So you go from one page to another, then from this page to another page you're linking to, then another page, and so on and so forth. You do it an infinite number of times, and you add a small probability, a very small probability, to jump randomly to any other node. So this allows you to solve the problem of disconnected parts, of nodes that have no incoming edges. So you have this very small probability to jump randomly to any other node. Otherwise, you follow the outgoing edges, and you do that infinitely. And your PageRank is the probability that this process ends on you. So you see that if you have a lot of incoming edges, then this random process of moving in the graph has a higher probability to reach you because you have many incoming edges. So maybe in the end, it will stop on you. But you see also that if you are pointed to by people who are by pages that are not important, then your probability is not that high. But if you're pointed to by nodes that themselves have a strong probability to attract this random walker, then it will make your probability even higher. So if you're pointed to by pages that are important, that are pointed to by many other pages, that are pointed to by many other pages, and so on and so forth, then your PageRank goes up. So then you might ask, so how do Google use PageRank? Well, basically, it's quite simple. They first compute the PageRank of all the pages on the internet using the power method. And then they create a subgraph of documents related to our topic. So when you do your search, you enter some words. They are searching all the pages related to that contain these words, and then they rank them according to the PageRank. So obviously, that was true in the beginning. That's really what they were doing exactly on the first version of Google. So you could even look at the PageRank score. So with each page, you have the PageRank score. But I think now you all know that they changed a lot the algorithm. Of course, they improved it by personalizing for you, by personalizing by language, personalizing by many different things. And so we don't really know exactly how it works today. So you remember that they said that it was search engine technology remained largely a black art. That's what they were saying in their paper. Well, it's still the case with Google because we don't really know what they use. But I was reading a paper the other day where they tried to retro-engineer how it works. So they were trying to understand what was really the score correlated with. And it seems to be still strongly connected to PageRank. So probably they use, and they say more or less that they still use PageRank at the core, but it's a personalized PageRank and with many other aspects that we don't know. But still the idea is a variant of the eigenvector centrality is also the KATZ centrality. So just quickly, this one is interesting in my opinion because it gives, so it's just a variation actually of the eigenvector centrality, but it gives a different interpretation also. So to help understand maybe how it works. So the original formulation is like this. So I detail here. So you want to compute the KATZ centrality of a node. You have this part which corresponds to the pairs, actually the nodes which that you can reach at distance k. So if you remember this, so well, and this is an attenuation factor which penalizes influence to distance, and I will go for it. So you will repeat for all the distance as long as possible. So it's a problem of convergence that you will solve with an eigenvector later. But if you want to understand it, how it is defined, this that you will repeat for all distances as long as possible. You will compute the sum for all the other nodes. So you're computing for I, you will compute for all the other nodes j. A parameter which decreases with distance. So something which is smaller than 1, which is between 0 and 1. So when you take the power k, you will decrease the value. So at distance 1, you will get the value itself, but then when you take the square, you will have something which is smaller and smaller and smaller and smaller. So for the nodes who are far from you, you will get a smaller value. So they will have less importance. And this part is computing the number of different paths from I to j of length k. Because if you remember this from the first class, we have said that the square of the adjacency matrix computes the number of walk that go from you to the other nodes, between each pair of nodes, with a walk of distance, the power. So here, if you take the square, it's distance, number of walk of distance 2. If you take the cube, it's distance walk of distance 3, and so on and so forth. And so, yeah, in the end, what you're doing is that you're computing the sum of paths to all the other nodes at each distance, multiplied by a factor decreasing with distance. So the number of nodes you can reach at distance 1 are the most important. But then if you can reach many nodes at distance 2, they will have less importance for you because they are at distance 2, but still they are important. And then distance 3, they are even less important. But if you can reach many, then it will increase your centrality, and so on and so forth. And actually, there is this relation with the eigenvector centrality that, if you remember the definition of the eigenvector centrality, it was the eigenvector centrality was equal to some normalization and the sum of the eigenvector centrality. And you see that here we are allowing to use any alpha and not just, so the alpha is the same alpha as here. So it's your coefficient that will say how much you lose importance when you go further in the network. So you can use any alpha, and it adds this beta. But if you set beta equals 0, and you set alpha equal 1 divided by the largest eigenvalue, then you get exactly the eigenvector centrality. So you see that the two things are correlated, but maybe it gives a different interpretation. So I presented these ones because they are the most typical one, but there are many other ones that have been proposed. The problem is how to interpret them, because these ones are relatively simple to interpret. We kind of understand what they mean. Some of them is much harder, and you could imagine many different variations on that. Sometimes they can be useful if you want to use machine learning to, for instance, I don't know, you want to identify some important node in the network. You know, for instance, in a social network, all the journalists, let's say, and you want to identify all the journalists. Well, maybe you will compute many centralities for all the nodes, and then you will automatically learn how these centralities are correlated with being a journalist. So maybe you know that you will observe that if you take the betweenness and the betweenness is high, the degree centrality is not that high, and another centrality that we have not presented here is high, and the other one is not high, then maybe it corresponds to a journalist. So that's why even if they are not always interpretable, it's interesting to have these centralities which tell you something about the position in the network. So let's finish this class with a little game. The goal is for you to guess which centrality corresponds to what network. So the more red, the more dark the value, the highest the centrality. And you have the list of centralities on the right. And can you guess? Oh, I don't have the numbers, but let's say it's 1, 2, 3, 4, 5, 6, 7, 8. Actually, it's pretty difficult, but some of them you can guess. You have intuitions, opinions. Yes?
8 is clustering coefficient.
The last one, clustering coefficient. Yes, that's a good hypothesis, because yeah, these ones are connected together. So they have a non-zero value, while the other they do not have triangles. So yes, probably. Sorry. Yeah. Okay. So maybe these some of them are very similar. Like these two are maybe the easiest to find next. Sorry. I don't think it's betweenness. So it's two centralities which are very similar that we have described. Yeah.
Closeness and harmonic.
Yes, it's probably that, and you can see this kind of circle. You see the center, which is dark, and then it goes more light and more light the more you go to the periphery. You have really this idea of a circle like that. Any other guess? So the other ones are really, yeah.
6 is degree.
1, 2, 3, 4, 5, 6. This one? Yeah, it's pretty hard because I think this one and this one are very similar. And one of them is a degree, but even I don't remember which one. Yeah. Which one? Sorry. 1, 2, 3, 4, 5. This one. Betweenness.
Yeah, because which is at the middle is very high.
Yeah, it's likely. Yeah, if we proceed by elimination, yeah, it has some important also here. This one, which separate this part of the graph, and this one is important. So that's likely. So I remember. So I try to help myself to help you. So this one is the degree. So yeah, pretty close from what you were saying because they are very similar. And this one is the KATZ centrality. And from that, maybe you can guess which one is, for instance, the eigenvector centrality, because they are similar. So I think it should be this one. Well, let's check the answers. So you have harmonic centrality and closeness there. You have the eigenvector centrality here, which is indeed quite similar to KATZ. And you have something which is quite typical of the eigenvector centrality, is this what we call sometimes the rich club phenomenon, which is that since you're important because you're connected to important nodes, then you might have some part of the network that vote each for each other, and so it makes some part of the network a little bit randomly very important because the importance concentrates there, and that's what happens here. The PageRank here and yeah, betweenness there. You see that the PageRank will give some strong. So we don't see very well on the graph, but there are some nodes here. Maybe you don't. I don't know if you can see them, but anyway. So that's why this one is important also, because for PageRank, many pages vote for him. Clustering coefficient on the bottom right, indeed, and I think everything is okay. Yeah.
Just to be sure, you talked about how a certain component can be randomly very important. All the way you computed the degree of centrality, it's all deterministic, or can you, with the same graph, say at the end have some different way of computing KATZ between this eigenvector?
It's a good question. No, it should be. So of course there is one exact solution. If you use if you take the eigenvectors, if you compute the eigenvectors, there is a single solution. So it's not random, it's not stochastic. But if you compute it with the power method, starting with random values, actually, I don't know. I haven't checked that. Maybe if it's really, if there is really something like if you have two parts which are really strongly connected and separated from each other and symmetric, maybe it's stochastic. I don't know.
But some of them, which one of them are? Some of them are still deterministic.
All the other ones are deterministic. Basically, you compute the degree, you compute it's just counting betweenness, it's just counting how many short paths you have, and yeah. So most of them are deterministic. Sometimes they are deterministic in theory, how they are defined, but the problem is that when you need to compute them on large graph, you need to do some approximation, and then maybe it's not deterministic. So simpler version. I hope this one can be, you can find the solution. Degree, betweenness, closeness, eigenvector. What are your guess? Yes.
I would say closeness is D. Because it has this.
D?
Yes.
The closeness? What are your opinions? And the other ones? What do you think the other ones? Yeah.
I would say the closeness is D because it's right in the center.
Yeah, I think you're right that the two looks a little bit similar, but closeness is more being really central. So closeness is, so you should have the strongest link rather in the center of the figure. So probably this one is closeness. Yeah. So probably betweenness, so networks. So probably betweenness is this one, yes, because you see that some important nodes seems to be bridges between different parts. Like there is this rift in the middle, and all these edges seems to be important. So yeah, I will vote for it too. And so we are left with these two. Yeah.
This is probably EIGENVECTOR.
Yeah, so we see with this rich club, and we are left with A, which is the degree, with just the color corresponding to the number of connections. So you don't see it very well, but yeah, degree, closeness, betweenness, eigenvector. And I think that's all for the lecture part for today. We have, I was asked by Christophe Crespel, who is the teacher of next Tuesday, and the week after also on Tuesday. He proposed some internship. So if you're interested, you can contact him quickly, of course, but he has a funding for these two topics. One is about finding communities of links, which is rather original. So you want to find, you see colors on links here, and you want to find groups of links that are grouped together, basically. Or another one, which is more graph oriented and more than network. So it's more graph theory aspect. But if you're interested, feel free to contact him. I will let this slide for some times at the screen. And so we now move to the second part, where I invite you to check on my website the exercises that I propose on computer. No, not that. This one. So we can make a short break, and then you have these two exercises where you will plot networks and compute some scores on them that we have seen Tuesday and today. So yeah, we can have a short break if you want, and then you can start that here.